Let's take three values that can either be 0 or 1. These values are given to a computer program, which also gets the expected output. The program then gives us an output value between 0 and 1 based on the input. Let's put this into a table to figure out the output. We can try to figure out the output by looking at the patterns in the three inputs that led to the output. I encourage you to pause and try to figure it out yourself. If the first input is 0, the output should be 0. If the first input is 1, the output should be 1. But if the second input is 1 and the first input is 1 too, then the output should be 0. And if the third input is 1, then the output should be 1 as well, irrespective of the other two inputs. So in our last example, the output should be 1. This can be hard-coded quite easily. But if we had 10 inputs, it would be much harder to find the pattern. If there were 500 inputs, it would be impossible to find the pattern by hand. In this case, we can use the neural network, specifically a multi-layer perceptron, to find the pattern and predict the output for new data. The purpose of this video is to show you how to make a multi-layer perceptron from scratch without tools like TensorFlow or PyTorch. You will be making a neural network with 3 input neurons, 2 hidden neurons, and 1 output neuron, like the one displayed. Before I begin with the code, I want to make it clear that it is necessary to know the fundamentals of neural networks such as weights, biases, forward pass, and backpropagation, as I will not be explaining them in this video. We will be using NumPy for matrix operations, so it's necessary to install it if you haven't already. First, we import NumPy. Then, we define our activation function, sigmoid, and its derivative. We define our input data with the example I started the video with. We intentionally leave one possible combination to test our neural network. We initialize our weights and biases with random values which will be adjusted in backpropagation. We define a function for forward propagation where Z1 is the unactivated hidden layer, A1 is the activated hidden layer, Z2 is the unactivated output neuron, and A2 is the activated output neuron, which will be the model's prediction. We then return all of these values. Then we create a function for backpropagation, taking in the number of iterations to train for and the learning rate. We store each of the values returned by the forward propagation. The error is the difference between the prediction and the expected output. Every 100th iteration, we print the error. To adjust our weights and biases, we first need to find the contribution of the weights and bias of the output layer to the final error. Then we find the contribution of the hidden layer to the final layer. With that, we find the adjustments to be made to the weights and biases of the hidden layer. Now we adjust the weights and biases by their contribution to the final error multiplied by the learning rate. We then call the backpropagation function, telling it to train for 10,000 iterations with a learning rate of 1. Finally, we define our testing data, which is the one example we didn't use for training, and we print out the prediction made by the neural network. Let's run the program. We can see the error gradually reduce. In the last line is the prediction for our testing example, which is almost the expected output of 1. Because the third input was 1, the output should be 1 as well. So that was a neural network in less than 50 lines of code. If you want to see more content like this, please subscribe.